Okay, Assalamualaikum. Let's start our class with recitation of Ummul Kitab Al-Fatihah. Okay, in the previous class, we have learned about a few things. We have learned about the classification of material and feedback on previous presentation. I talked about the classification of living thing and then classification of solid material, and I give you this, what we call this image, where you have metal, polymer, ceramic, and then you have composite, and then you have advanced material. And then after that, you have this, what we call the properties, the 6 properties. When we talk about material, this the common properties that people check. And then we go and talk about the metal. And at the end, we also have the question time. So for today, we will talk about the ceramic and polymer. Okay, about ceramic. We start with the definition of ceramic. Okay, so let me go here. So let me put ceramic here. Ceramic. Okay, so the definition of ceramic. What is ceramic? Definition. Okay. So ceramic is basically a compound between metallic and non-metallic. It's a compound between metallic and non-metallic. And this metal, right? So the non-metallic part, the most common non-metal element that is combined to make a ceramic is they are like the common one, which is the oxide. You have oxide, and then you have also the nitrites, and also you have the carbide. So the example for this ceramic, when you have this metallic and the non-metallic together, is basically, for example, you have this aluminium oxide, or we call it alumina. Normally alumina, Al2O3, or we call it as alumina. And also you can have something called and also you have something like a silicon dioxide, or SiO2. This normally we call it silica, the common name for that. And also you have like silicon carbide. Okay, so you have like SiC. Okay, so that is what is not common. I mean that when we talk about the non-metallic part, you can see most of the time they are oxide, they are either nitride and also carbide. So that is one definition of this what we call the ceramic, but that's only one. The first one here, the compound between metallic, plus okay, this definition plus also what normally people call traditional ceramic. Normally this is basically when people talk about clay and also the what we call the mineral. For example, the clay and mineral. So that's also under the ceramic. Yes, of course, clay also have this silicon oxide composition inside that. But normally when people talk about traditional ceramic, they talk about this clay and mineral, those who have been used by ancient people before the modern era lah. So that is basically also one of the not definition, meaning that the part of definition of ceramic. So let's go down. So and then what else? And then also example for this clay and mineral is like what we call the porcelain lah, and also the cookware, and not cookware, I mean that the earthenware and so on. And then also under the ceramic category also they have cement also ceramic, that also ceramic. And also under the ceramic category is what we call glass. Okay, glass also under the category of ceramic. So basically this sort of like a big definition of ceramic is it's not idea, I mean that is compound between metallic and non-metallic, traditional ceramic, cement or glass. So that's when we talk about ceramic, this is what we ask. Okay, about the mechanical properties of the ceramic itself. So let me do here properties. properties of the ceramic. So ceramic have this what we call, let me make it smaller so easy for me to write. Okay. Okay, so ceramic, when you see ceramic, ceramic is, we can say, is relatively what we call stiff and strong. We can say it's stiff and strong. Stiff and strong. So it's basically what we call, is comparable to metal. In certain way, it's more or less comparable to metal. Plus, okay, plus. Yeah, so let me put this comparable to metal, Plus the ceramic also hard. Okay, hard. Okay, metal is not hard. Metal is ductile. Okay, metal is ductile. That's why you easily can scratch metal lah. But ceramic is very difficult to scratch ceramic using your nail or whatever. So that's the thing. And historically, ceramic is very brittle. I mean, long time ago, when people make ceramic, like the potter whatsoever, it's very brittle, extremely brittle. But nowadays, they perfecting the thing, adding here and there. So now the ceramic becomes stronger and stronger lah. Stronger. I mean, it's brittle, but still it's not as brittle as before lah. So it's already engineered so that it has this what we call improved resistance to fracture. So nowadays, so let me put nowadays, improve what we call improve fracture, improve resistance to fracture, improve resistance to fracture. Okay, because why? Because ceramic, one of the most problem with the ceramic is that, let me put here, so even though it's stiff and strong and hard, the downside for this is ceramic is brittle. Downside is ceramic is brittle. Wait for a minute lah, I need to do this. Okay, sorry for that. Okay, so that's why nowadays, if you see, for example, people for the in order for people to use this ceramic in the daily life, they improve the engineer so that it becomes stronger. For example, like the cookware nowadays. For example, like this thing. Okay, so for example, this coral. Normally, this is not really porcelain, but yeah, you can see the sound. The sound itself is you have this distinct sound, and it is very strong. I mean, normal glass, what we call normal plate, when you sort of like hits here and there, it will crack easily. But this it take more resistance to crack, and of course when you try to like left it like that, like down, then of course it break also. But at least it's more resistant than before lah. To show you, one of the properties of ceramic is that it's very brittle lah. It's very brittle. Okay, so what else? So that's why nowadays people use this resistant to fracture. People use it to create this cookware and also the cutlery lah. The cookware and also for the cutlery lah. Cutlery. We will go to these mechanical properties again about the brittleness, but before we go that, I will explain just in general overview first. So another mechanical properties of what we call ceramic is that it's insulative. It's insulative to heat and electricity. So you can use ceramic. That's why when you want to create, when you want to sort of like heat something very, very hot, you use ceramic. You use clean. People call it clean. Yeah. So like this. Let me draw this thing. This is predictable. So let me make this thing. So you go here and go here. So let me go here. So kiln, KILN. Okay. So ceramic kiln. Okay, so you can see when you want to do something very hot, you need to use the ceramic as a container. In fact, if you want to do if you want to sort of like melt the metal, you know metal is strong and it takes a lot of melting point, right? You need to melt the metal inside the ceramic kiln. You cannot just melt the metal inside the metal. You need to do it in this ceramic kiln. For example, kiln for metal forgery. Let's say I put like that. Kiln metal forgery. No, metal ceramic kiln. Ceramic kiln and then metal. So yeah, where is the thing? Metal. Mana gambar tu? Metal process. They are metal making metal. Yeah, like this. You want to, yeah, like that. Okay. So basically, in order to melt metal, you need to put it in the ceramic. So that's one of the distinct feature of the ceramic, because it have this insulative. It's very they have very high melting point lah compared to other polymer or metal. And also, it's also this have high resistance related to this previous mechanical properties. It have high, what we call not high, I mean that it have resistance. So it's resistant. It's more resistant to high temperature. Not only on the temperature, it's also more resistant to this environment, harsh environment. For example, chemical and so on, chemical inertness. It have this chemical inertness, and also harsh environment. Okay, let me put yourself here. It's already go somewhere, so like that. Okay, and also in terms of the optical. Okay, let's go down. In terms of the optical. Okay, the ceramic may be transparent. Ceramic can be transparent. For example, we thought one of the type of ceramic is glass. So that is what we call the transparent optical. The optical properties of the glass is transparent. So glass is ceramic, and also it can be also translucent. For example, if you scratch the glass, right? You have glass and then you scratch it, so it's still ceramic. It's still maintained as ceramic, but you get this ceramic with scratch. So we call it scratch glass, and it also can be opaque lah. Differ with the metal. Metal is totally opaque lah. Okay, so that is for example, for opaque, like a brick lah, the one that you make the house. So that's opaque lah, ceramic. Okay, and some ceramic oxide, they have this magnetic what we call magnetic properties. Only some lah. Some have magnetic properties. For example, the ferrum oxide. Normally, when we talk about something that have magnetic, they must have some sort of like iron, cobalt, or nickel. So, for example, the ceramic oxide, Fe, what we call 304. So, this is iron oxide lah. Oxide ceramic, we call it oxide ceramic. And even though we know that iron, ferrum, is metal, but now it's combined with some oxide. Oi, alamak. Sekejap because it's combined with the what we call the oxide, so you get this combination, so that's become a ceramic. So now we have seen this, what we call the generic idea about the ceramic itself. What is ceramic? If you go up there, so let me bring here, and then maybe I make it a little bit small. So you can see here the ceramic. We learn about the definition and also the mechanical properties of the ceramic. And I want to talk a little bit about the brittleness of the ceramic. Okay, because this is one of the most common, the most what we call the distinct feature of the ceramic. Okay, have you seen this? What we call, I think most of you have seen this, right? If I put here, you have seen Dalgona Squid Game. So you have seen this thing, this guy holding this thing. This is Dalgona. For those of you who have seen this movie, so at least you know lah. So you see this biscuit they have this brittleness analogous to the ceramic. Of course, this biscuit, this Dalgona is not a ceramic because it's made from the sugar. It's made from the sugar. So it's, but the idea is almost similar because the molecule inside this Dalgona is non-ordered. It's not like metal. It's disordered, but it's solid. Disorder, but it's solid. It's as if something that's very molten, very hot, the liquid form, and then is suddenly frozen. So the molecule doesn't have time to rearrange themselves. So that's why the entire solid that you get later on, we call it sort of like amorphous, meaning that the molecule inside is disorder, so that there are no preferred exist for crack. So if you crack some at one point, then the others also, it can just go here and there lah. So this Dalgona, so you know how difficult for you to sort of like to cut this thing, to cut this what you call this thing. So this is a behavior of brittleness. They have like, you don't see the when they crack, they are no sign for that. If you have metal, it's different, right? If you have metal, if you try to do it, at least it will become ductile first. If you have big metal bar and you try to pull, the metal will sort of like thinning in the middle. But ceramic, if you try to pull the brick, it will just break like that. It will not like elongate more or less like that. Okay, so that's one of the properties of this what we call this ceramic is equivalent to this thing lah. So let me put here. What is this? This there. So this where I make this here. Okay, so let me make it down first. Don't worry that. So I have here. Okay, so I thought some analogies of the Dalgona and the ceramic. So in fact, you have this thing. So for example, this Dalgona that I make. So if let's say you have seen this, you see this what we call the normally you have the pattern, right? The either square or round or triangle. So if you see there, they are sort of like what we call the dent there. So the reason why it's easy for this what we call for the people to break here is because of the concept of crack propagation. This is the same idea in the ceramic. But before I talk about that, let's talk a little bit about this how this was made lah. Because the idea is more or less like the glass, how people make glass. But glass they use a sand. But this they use what we call the sugar. So basically, in order to make that, is you just give a brief overview lah. So let's say I put Dalgona, just brief overview. So the only ingredient that you need is that what? Is that you need to have, you put in sugar. So sugar. And then when you have sugar and then you sort of like heat it. Okay? When the sugar heat, it become caramelized. It become caramelized. Okay, normally for the sugar, for the table sugar, which is sucrose, for example, table sugar is a sucrose, the caramelization temperature is around 160, 170 Celsius lah. For the ceramic, for example, glass, you use sand. Okay, sand. They use sand. Sand is the main ingredient for the making glass. But here you use the what we call the glucose, the sugar lah, the sugar. But for the ceramic, for the glass, you need very high temperature, 1000 and above. But for this Dalgona, you only need 160, 170, so that you can make it in your kitchen. So when you caramelize, you get something like liquidy like that, and then you add what? And then you add, so inside this thing, when it's already caramelized like that. So you have this distinct color of caramel, right? So after it's caramelized, what they do is that they add what we call with the carbonate. They add with the carbonate. Normally we use this what we call baking soda. Baking soda is basically a carbonate. When you sort of like, when this baking soda is basically the what we call the can you see that? Oh, you cannot see. So I need to make here. So let me make here small. Okay. Okay, so like that. So when the baking soda here, basically they have this what we call these properties. Not properties. I mean that when you heat it, when you heat the baking soda, the reaction, the chemical reaction is basically the baking soda is sodium, and you have this carbonate, and then let's say when you heat it, you get this what we call Na2CO3, and then you cannot see, right? So I need to make this small. Make it small. Oh, I just bring this here a little bit. This I bring you here. Oh, there are a lot of things. So I bring this thing here first. Okay, I bring this here. Okay, and then maybe you can go here a little bit. Okay. So the idea is that you have this when you heat this thing, heat the what we call this carbonate. You have this, and then you have what we call CO2. You have H2O lah, H2O first. You have H2O, and then you have CO2. Okay, this carbonate also used when you make a glass, when you make a ceramic. But of course, they don't use baking soda lah. They use other stuff. Later on, I will discuss. So this is when you heat the baking soda lah. When you heat the baking soda, what happen when you heat baking soda? So let me put here, so much easier for you later on. So when you heat, you get something like this. Okay, so the most important thing here, the reaction here, is that it create this thing. They make they develop this CO2. CO2 is carbon dioxide lah, so it's like bubble. It's like a gas bubble bubble. So when you have this gas bubble, and then you have this caramel inside this what we call whatever pan that you do, the gas bubble will sort of like trap within this the molecule of the molten glucose and molten sucrose. So that cause this what we call this your caramel become bigger and bigger. It become rice. We call it rice lah. That's why you use this baking soda. Normally when you have for example, if you want to make a bread, the idea for bread is also same, but they use yeast to make a carbon dioxide. So if you have the microscope, and even if you look in the naked eyes, you can see on the bread you have like hole, right? So that is the carbon dioxide bubble that is trapped within the bread. So that's why bread you can see a bigger and fluffy lah. But in this case, baking soda, they don't use. They use chemically. Here you use what we call the yeast. The yeast, a microbe. It takes a longer time. But for the baking soda, it decompose. When it decompose through heat, it also release the carbon dioxide. So that's make this what we call this caramel become bigger and bigger. So before we go further, so this is basically going to this is basically sucrose. They break down into glucose and fructose plus fructose. Okay, so sucrose is not just like one molecule, it's just two molecules combined together. It's disaccharide. So when you heat, it will decompose, break down into glucose and fructose. And this sucrose, if you look here, the sucrose have this what we call, you can decompose it at 160 to 170. Some sugar doesn't they need lower temperature to break down. For example, let's say you have a fruit. Inside the fruit you have fructose. That's why fruit. The sugar inside the fruit is fructose. So for the fructose, normally the temperature for it to caramelize is around 110. That's why when you have like what we call the fruit, like what we call like the carrot, whatever, you try to caramelize this carrot, you just need a very low heat. So for example, let's say I put here, just here. So for example, carrot caramelize. So let's say put here. So you can see here, It's same thing. They have this what we call this thing, the color, the brownish color and that thing. So when you do this thing, it take like a very less heat lah compared to when you want to caramelize the sugar, the table sugar. So coming back to this, so let's go to here. Go to here. So what we learned here is that basically the concept of making Dalgona is more or less the same as the concept of making glass, because you need something first. Glass, you need sand, and also in glass you need something, but not baking soda, but we call it flux. The flux, later we will discuss a little bit further. Flux, the purpose of flux is basically to lower down the melting temperature of the sand itself. Okay, so you need to have ingredient, and then you also need to have something else in order to make things happen. So glass, you cannot just make glass by what we call by heating the sand. Okay, you need to have other ingredient to make it clear glass lah. Okay, so now we talk about previously we talked about this what we call the brittleness of the what we call the ceramic. So here, as I said, this thing, when you get the Dalgona here, whenever you get the Dalgona here, let's say I put this thing, the Dalgona, let's say this Dalgona, as I said, the inside here, the molecule inside here is disordered, or we call it non-crystalline, okay. We will talk about crystallinity in detail later on. But for time being, just imagine that inside this Dalgona, there are like a molecule here and there. So it's not ordered as what we see in the metal. Okay, same thing like a glass. So when I talk about this, is equivalent when I to the glass lah. Okay. So here, if you have this, for example, you have this sort of like a then you sort of like as if you split the molecule away, so it make it easy to break. That's why for this thing, if you take this, what we call the toothpick in the picture, in the what we call Squid Game, they use this toothpick to break here because it have this crack propagation. So this, what we call this round, is easy because you have this defined path for the crack to happen. But if you have something that is very complex, for example, the structure is very complex, for example, like this what? I don't know. This is CHEN, CHEN1311. Okay, that is your course code, CHEN1311. So if you have something like this, you have sort of like straight, you have like curve, straight curve, that is very difficult to sort of like to break it down, because as I said, the crack will propagate whenever is the dent happen lah. For example, here, if you, for example, here it's already cracked there, so this happen because it's very difficult to sort of like crack on the defined path that is have curvy and straight line. So that's one thing about the thing. So let's talk a little bit about this crack, the micro propagation. We call it micro propagation of the crack. This we talk on the brittle. Let me go down. Okay. Let's say you want to cut the glass. Let's say you want to cut the glass. Let's say we put here. Let me put here you there. Let's say we want to cut the glass. Let's say you want to glass cutting. Okay. So glass cutting, how you cut the glass is almost the same how you do for this. For Dalgona, you need to make a dent and then you cut the glass. So this is done. Let me put down here. For example, let's say you have this thing. You have the what we call the glass slide, and then you want to sort of like break into two. So the easiest way to do this is basically to crack it in some defined manner lah. So for example, let's say I try to crack that. So let's say I bring this thing, so it's easy. So make it bigger a little bit. Let me bigger a little bit. Okay, so that you can see. So here, and then you have glass here, and then let's say I have this thing. If I want to break something like this break into two, break into two. If I don't do anything for this glass, if I just do like this, if I hold this and I do like this, so you can see there are splinter there. So there are splinter there because the molecule inside glass is like in Dalgona. They don't have this preferred orientation. When they are cracked, they just go everywhere. But if you make a dent, for example, I have another one here, and then this I remove somewhere, go there, and then I try to sort of like make a dent. So for that, I use this what we call this knife, and then I just let's say I put here. I need to be here. I hope you can still hear me. So I make in the middle here. So I want to take this knife, and then just simply sort of like scratch the thing. Okay, so let me do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Because your class code is 13, 13, 11. So I use 13 lah. Okay, so now you don't really see the dent there. I mean, I don't know whether you can see or not because this is, but they are sort of like a mark, the scratch mark. We call it scoring. The term that I did just now is scoring. SCORING, scoring. So now if I do like this, no, there are no mark. There are no mark yet. There are no mark at all because I don't do it very hard. There are no mark. Normally when you want to do scoring, you don't use this metal. You use there are specific blade because this is metal. Normally people use a diamond cutter, or they use this tungsten carbide. Okay, so let me do again because I don't see the crack, the dent just now. So let me do again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No lah, but let's see, because I don't see the what we call the scratch because this maybe not sharp enough. So it's not about sharp, it's about the slip. Because the ceramic is hard. One of the thing about ceramic is hard, so you cannot really use. If you have something sharp, it's not. If it is soft like a metal, it's ductile. Then even though it's sharp, it cannot like scratch this thing, the glass. So here from me, I don't know whether they have some scratch, but very little. I don't know whether you can or not. Yeah, they are not scratched. So you can see, because there are no scratch there. So maybe I need to use a different, knife. Let's say I take this knife. So this knife, okay, the knife that you use. The new knife that I use now, this is blunt. This is blunt. It's not as sharp as this. The one that I used just now is sharp. So maybe because it's sharp, it doesn't, it sort of like slip here and there. But now this is blunt knife, really a little bit blunt lah. So let me see, and I need to focus a little bit. I need to go here. Okay, here, and then let me cut it. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11. Okay, so now you can see they are sort of like mark, right? So they are different when you use a sharp knife and also when you use a blunt knife. Even though sharp knife is desirable, but sometimes you want not sharp but hard. When it's blunt, they have many. When the knife is blunt, they have many sort of like point to scratch. For example, if I show you, if the knife is sharp, you have only sort of like one point here in order to scratch the surface. But if your knife is blunt, for example like this, you have like many point to scratch a surface, which is make it more easier and more successful lah in order to blunt this thing. So sharp knife is okay if you want to cut something that is soft. But if you want to cut something that is what we call hard, like ceramic, then you need something very sort of like not only sharp but also hard and also have some ridges lah. That's why when you see anything like this, for example, let me put there so you can still see the image, right? For example, glass cutter. Glass cutter. If you look glass cutter, okay. So the glass cutter here, you can see it's not really sharp here. You can see it's not really sharp. So let me put here. So this glass cutter is not really sharp, but it's hard. There are some sharpness, but the most important thing is hard. Normally they use tungsten carbide or they use diamond. Diamond for cutter. Glass cutter diamond. Let's say diamond. Okay, so even diamond. So you can see there are something, but it's not really super sharp lah. It's just hard. Remember, there are different between sharp and hard. You sometimes need. So you can see here. Let me close this first. So you can see here, you can see here, right? This is not really sharp. It just have this sort of like kasar. Kasar apa? What is kasar?
Coarse.
Coarse. The most important is coarse because you can make a lot of dent. Okay, so here, let's see whether I can cut or not. So you see there are sort of like mark there, right? So let me do like this, and then I do like this. So you can see it just break into two cleanly. Okay, so the reason for this, okay, let me talk about the reason behind that. Okay, because this is one of the properties of ceramic lah. That's why we think. So let me put down. Okay, here. So first you need to understand glass or ceramic or Dalgona is non-crystalline. Non-crystalline. So when something non-crystalline, we call it amorphous. Okay, amorphous. So this normally occur when the liquid cool. Alamak, tak nampak. So I need to put this thing. I need to make it here. Let me put here. When the liquid cool rapidly, so that the molecule doesn't have time to rearrange themselves lah. Okay, so unlike crystal, so for example, unlike crystal, amorphous have this what we call this the isotropic. Okay, the amorphous, they have this isotropic properties. Isotropic properties mean that iso mean equal, meaning that the properties is equal here and there. So there are no preferred axis of the direction in glass. Okay, if you have some, for example, like a wood, for example, like a wood, just for example, wood. In the wood, you see sometimes you see this grain, right? They have this thing, and then you have a grain. So this grain boundary, they have this orientation. So for example, you can see the most of it goes this way, right? So this way. So you have this preferred orientation, meaning that it's much easier to split this wood into half from this. So it's much easier to split. It's stronger when you pull. When you pull, it's strong, but when you try to kepak here, like this, is weak lah. Later during the composite part, we will discuss this in detail lah. But these isotropic properties, meaning that when you have some crack, when you initiate some crack, then it can go anywhere. That's why when you do this thing, the term is scoring. This is what we call the scoring. Scoring, and normally people use the glass cutter. Glass cutter, normally the tips is made from the tungsten carbide, which is very hard. This almost we can say equivalent to the diamond lah. Tungsten carbide is synthetic, they create it. It's like alloy. So this more or less, the hardness is more or less like diamond lah. Diamond is more or less like diamond is more harder lah. Diamond, the hardness is more or less and also they also use diamond. It's not they use a normal diamond. You can synthesize diamond. You don't need to go and find the diamond under the earth. No, the diamond that is used in the industry is not the natural diamond. They synthesize it. You can synthesize diamond. We call it industrial diamond. Later we show you lah. I don't have here, but basically it's just sort of like you have like a tool, like for example this blade, and then they sprinkle the dust of diamond here, the real diamond, the hard, and not the real diamond, I mean that the synthetic diamond here. And then because of that, and diamond, they have a lot of diamonds, small diamond, they have a lot of like, it become coarse lah, C-O-R-C-E, kasar, so it's easy to squash. So that is scoring. So when they are stopping, when you are scoring, if there is what we call the line of what we call when you sort of like make something like this, for example this glass, and then you make scoring here, color like this, okay, scoring here, okay, scoring here, and then you, when you start put the knife here, when you start, let me put the color, okay, when you put knife there, so you induce the local stress on that particular place. And when you do that, they have what we call you have a sort of like crack there, so as if let's say you have something like this, this color, no, this is not really working very well, so meaning that you have this, and then you induce some crack here, and then the later you become, this crack will be propagate and go like this lah. Yeah, you become, they have this head of direction, they have this head, what we call head for crack propagation. Okay, so basically when you scratch, then you try to break, when you try to sort of like push or whatever, this thing, the one that I show you, the crack will propagate along the axis, because now you are creating this what we call the preferred axis. Previously there are no, previously if you do, as you see, it's splinter, but now when you have this crack, then you have sort of like a path for propagation to happen. Okay, now night is 9:14. So today maybe I just do for ceramic only. I'm not. I think we don't have time for polymer. So I will complete the ceramic today. Okay. So so that is basically about crack propagation. So one of the thing about glass is that it's brittle, and you can sort of cut it by using this coring method. So the reason, so when thing like glass, disordered, non-crystalline, there are method to cut it. It's not, for metal it's easy. Metal you just cut, then you can just ni lah. It's not really easy lah, but at least it will not crack like that lah. It will not crack like that. Okay, so let's talk a little bit about glass. So let me sort of like go here first. Okay, let's talk a little bit about glass, because today we just focus on ceramic only. Glass is under ceramic, so we talk about glass. So let's talk a little bit about glass. About glass. Okay, glass. What is the composition of glass? Because we want to sort of like combine what we have learned from this Dalgona and sort of like the glass, the real glass itself. So in the glass, as I said, you need to have main ingredient. The main ingredient in glass is basically main. So let's put silica. Silica is basically main ingredient lah. Ingredient. Silica is main ingredient lah. So yeah, okay. So the most common is sand. Most common is sand lah. Sand. But also it can, as I said before, this ceramic is normally amorphous, meaning that non-crystalline. But also this silica can occur in crystalline form in nature, which is the one that is quartz lah. So sometimes you see the crystal like this, right? Something like this. So okay, normally the sand is amorphous, but there are times that the sand can be crystalline. For example, this what we call this quartz crystal. Okay. Okay, so you can see here, they are like a crystal. You have this defined plane, defined face, surface. But if you see sand, sand doesn't have defined surface. The reason why you have this defined surface like this, here, let me open here. The reason why you have defined surface here, because as if, not as if, the molecule on that surface is ordered. It's ordered, okay? In sand, it's not like this. In sand, is just here and there. But in here, on the surface here, on where the plant is sharp, then you know the molecule is very sort of like arranged very periodically, regular arrangement, like the metal that we see just now, previous class. But about crystallinity, we will discuss in detail later lah. Okay, so that's the main ingredient for the silica. But as I said, in the making a Dalgona, you also need this baking soda, right? So in making glass, you need something what we call the flux. The flux. Okay, so you have two ingredients. So these two things you need, more or less two things lah. Flux. Flux is, what is flux? Flux is normally the function of the flux is to lower down the temperature of the melting point of the sand lah. To lower, function is to lower the melting point. During process lah, during glass process lah, glass processing. Okay, so that is the purpose of what we call, let me make it bigger like this. So that is the purpose of what we call the flux. And normally the flux, they use what we call the soda lime, and then they also use soda ash, and then they also use the potash lah, okay, the potash. So sometimes you heard the word limestone, right? Limestone ni is basically batu kapur lah. Batu kapur. All of you is local, right? So I think you understand lah. Batu kapur. So it's basically, they have inside this batu kapur or limestone, they have this what we call carbonate. Okay, carbonate. So when you say about what we call this, when you see something like this, for example, let's say if you see something like this thing, this is kapur, this is chalk, the chalk is made of a calcium carbonate. It's come from this limestone lah, calcium carbonate. So it's made, the chalk is basically made from the calcium carbonate lah. Let me, how to make, okay, so for example here, the chalk, so you have something like this. So that is made from the calcium carbonate. Okay, calcium carbonate. Soda ash, for example here, so that is basically when we said about this soda lime, so that basically this lah, calcium carbonate normally. When you talk about soda ash, it's basically sodium carbonate. It's sodium carbonate. So that is basically ni lah, sodium carbonate. So sodium carbonate normally, the reason why they say ash here is basically how they get this is basically they go and find a plant that is grown on the soil that have a lot of sodium. So they take that, what we call, the plant, and then they heat it, they bakar, they sort of like they heat the plant, and then that ash have this sodium carbonate lah. So that's the idea of how they get the soda ash. Potash is basically potassium lah. Potash is potassium. So so the idea of flux is to sort of like lower the temperature of this what we call the glass making process. Okay, so now about the glass, there are many type of glass, but I want to talk about two type of glass. The glass that you see just now here, okay, the glass that you see just now, and the glass that make a normal window, not your car, but normal window, is basically, we term it, let me go here, let me put here, I think I want to do here, and then I want to put you somewhere, no, I put here you, okay lah, here. Okay, let me talk about a little bit glass, the last part. Let me talk about the glass itself. I mean the classification of glass, some classification lah. So glass, you can have what we call one, soda lime glass. So soda lime glass is basically the normal glass that is, you see this lah. For example, making this the glass that I show you, the what we call the glass slide, the microscope slide. This is microscope slide. So soda lime glass. So soda lime glass is basically 70% silica, and they have this what we call 16% of soda oxide lah, soda oxide. Okay, soda oxide and 5% lime, maybe 5% lime, and so on lah, and maybe some potash lah, some very few potash, magnesia, alumina. So basically this alumina, so basically the one that I put like this is basically very small amount lah. No, 5% 5% is 5% lime, and then the potash, the one that I put in this red thing, is in the very small amount lah. So that's soda lime glass. The normal glass that you see around you is basically made from this soda lime. So this is the ingredient lah. You have silica, main ingredient, and then you have soda flux to help to make the thing. So the advantage for this, the glass is basically is inexpensive lah. It's expensive. Example for this glass is basically windows, and in the bottle, making bottle. So that is the thing lah. But the problem so this the advantage I put in green here. It's expensive, and then also easy to melt and shape, and also have most widely used. So that's one the advantage of this soda lime glass. But there are also disadvantage. So I put disadvantage here. Disadvantage. Okay. So the disadvantage of this, it has a very poor durability. That's why this thing is easy. I can just use my hand to break the thing. Okay. And the second one is have a poor thermal shock resistant. Okay. So what does it mean by thermal shock resistant? They don't use, industry doesn't use this type of glass or the lime to make your kitchenware. Thermal shock resistant meaning that you can heat it, and then you cool it, you heat it, you cool it, heat it, cool it, like that. Many times lah. So it's still so they don't have this thermal shock, because when you heat something and then you put it into the maybe in ice bath or whatever, the glass have tendency to crack. Okay, because for this soda lime, they have tendency to crack because they have this very big thermal coefficient. They have what we call the reason for this. The reason for this is because they have larger coefficient of thermal expansion. What does it mean? Expansion. What does it mean is that if you have, for example, let's say this glass, you heat it, and then after that, straight away, you put it into what we call into the ice bath. Let's say this ice bath, water lah. Let's say you put in water. So you know when you heat something and when you cool something, the thing become kembang kecut, expand, contract, right? So if you can look here in this wall. So if you have this large thermal expansion, meaning that when it's kembang, when it's expand, it will go very big, and when it's contract, it will also the distance. I mean the amount of its expand and the amount of its contract is big. So when this happen, and when you do it cyclically, mean that many time, it will induce the local stress around the glass itself. So you kembang kecut, habis lah macam tu. So that's why this soda lime glass have poor thermal shock resistance because of this. They have this large coefficient of thermal expansion. So the second type of glass, which is this maybe the last for the glass lah, because there are many type, but I think I just focus two lah. Second type of the glass is boro, and let me put cantik sikit, because this for your notes, right? So that's why I can do fast, write like this very fast, but it's difficult for you to read later on. So that's why I need to take time to this thing. So this is borosilicate glass. Okay, so borosilicate glass, the what we call the ingredient is basically 70%, not 70, is basically 80, more silica lah. 80% silica, silica, but the most important what we call important ingredient inside what make this different than the soda lime glass is basically they have this 13 around 10 to 13% boric oxide, boric oxide, and then you have this what we call, you have the other thing like potash, and then you have this potash, and then maybe you have also the alumina and so on lah, potash and alumina, but in this in the very very small amount lah, this I put in the red here. Okay, but the main thing you have boric oxide. So this the advantage for this example example is the labware lah. For example, the lab, if you go to the lab here, like let me go to here, if you go to labware, so all this labware, all these thing is made from borosilicate, because in the lab you heat something and then you cool something, you heat, you cool, you heat, you cool. So you cannot use soda lime. You need to use something like this, borosilicate glass. Borosilicate glass have very low thermal coefficient. So that's the difference. So let me coming back to this. So let me change this. So so example, labware, and also in your kitchen you can see pyrite, right? Pyrite. I don't know lah. Sister maybe know lah. Brother also know pyrite. I mean kitchenware lah. Kitchenware glass. Kitchen glassware lah. Glassware. So pyrite is basically the trick name only. But that's the same lah. So basically this thing, the advantage is have a very good very what we call. They have advantage. Very good thermal resistance. Because of what? Because it got a low coefficient of thermal expansion. Okay, low resistance of thermal coefficient, so that it more resistant to the temperature shock. Compared to the normal glass. Okay, normal glass is this thing lah, the one that we see before, we learned before, this thing. Soda lime glass is the normal glass lah. Borosilicate glass is the specialized glass that people add borax on that in order to reduce this thermal coefficient of the expansion lah. So that's why you can see this borosilicate glass in the what we call in the lab, and also in your kitchen, the pyrite. Okay. So that's why people like to use this, the ceramic, this clay, the porcelain or whatever. This far higher better than the glass. But the glass, when I said about the glass, one of the thing about the glass, appeal about the glass is because it's transparent. This not transparent. So even though this good, but something they want to see inside, right? So that's why they use glass also, this glass. To make a kitchenware. So of course using this ceramic, this type of ceramic, porcelain or clay, whatever, is much durable. But this have this optical appeal lah. So that's the thing. So that's basically about the ceramic and so on. And during the Iwana presentation previously, Iwana talked about this thing. Let me put here. Iwana talked about the porcelain and so on. The brick and so on. So all this ceramic, all this ceramic. So also we can see Ainul also talk about ceramic. Ainul talk about what? Ainul talk about this what we call earthenware, the cookware and so on. And you can see different temperature will create a different thing lah. So about the process, I will explain later lah. During when this early stage, we just give a generic overview of the ceramic. But later we will go maybe how to process the ceramic. Okay, so now it's 9:30. So maybe I just do quick question for question time. Quick question only. So let's go to the question time. So let's go question time now. Okay. Because it's already 9:30. So let's do question time. Okay, questions times. Okay. So the first question. Okay, what the question Okay, just brief just very brief. Tell me properties of ceramic. Anyone?
Me.
Okay.
Me.
What's your name?
Alif Mukri.
Alif Mukri. Alif Mukri.
Right.
Okay. Mukri, tell me the
Yes.
properties of ceramic.
Okay, so first of all, it is very stiff, strong, and hard. But compared to metal, metal can be easily stretched, which means that if you try to stretch it, it will be thinning at the middle. And the second one is ceramic is very brittle. Means if you try to stretch it, it will break immediately. So nowadays, people has been manufacturing improved resistance to fracture to produce convenient stuff like cookware and cutlery. And then the third one is ceramic is very insulative to heat and electricity, which means more resistance to temperature and harsh environment. And when it comes to optical terms, ceramic also has transparent like glass, translucent like scratched glass, and opaque like brick. And lastly, some have magnetic properties like oxide ceramic.
Okay, thank you, Ali Mukri. So that's a basic question time for the 1%. So the second question, because we need to go fast. Second question, tell me the relationship between Dalgano and glass.
You wanna?
Okay, Iwana.
Okay. So in the Squid Game, they use Dalgona candy, and the players get shot when they break the glass. So the property that the Dalgona candy easily break is the same property as glass. This is because when you heat glass, it will melt, and then when relation to the Dalgona candy, it is the molecule inside the Dalgona candy is very disordered. This is why when it breaks, it has a very high high crack propagation, which means when it cracks, it goes in various directions. And also, when Sir said about the Dalgona candy, it is because the molecule is disordered, but it suddenly turn molten. This is why when it breaks, it is very brittle. Same with glass. When you heat glass, you can see that there are when you heat glass, it melts, and then when the similarity between Dalgona candy and glass is that in Dalgona candy you add baking soda, but in glass heating you put flux. Flux is what you use to lower the melting point of glass, which makes it easier to stretch, and you can form shapes with the glass.
Okay,
That
thank
is the same thing.
Okay, thank you, Iwana. So the third question, tell me what happened during cutting the glass. Anyone?
Me.
What's your name? Your name?
Irdina.
Huh?
Irdina.
Irdina. Irdina. Okay. Your answer?
Okay. When cutting the glass, there are two okay, sorry. Okay. When cutting the glass, we have to use blunt point because when we use blunt point, it has many points to scratch, so it has a bigger surface for it to sort of break. But if we use sharp point, it only has one line to scratch, so it is very it has a thin surface so that it is harder to break it.
Okay, thank you.
And then for usually for glass cutter we use tungsten carbide and diamond that is produced for cutting the glass. Yeah.
Why they use custom carbide and carbon? Why?
Because it is very hard.
Yeah, okay. So it's hard, Okay, thank
Yes.
you, Idina. So last question for those who are in this, what we call in this thing, Okay, tell me two type of glass. Anyone?
Me, sir. Me, sir.
Ridwan. Ridwan first, Sorry, Aiman. Okay,
Uh,
okay. Ridwan, okay. Ridwan, okay.
First, soda lime glass. I need to tell the properties or not?
Just give some idea lah. What is soda lime glass and so
Yeah.
on.
So the soda lime glass, the advantage is inexpensive, easy to melt, and widely used in manufacturing. While the disadvantage for soda lime glass, poor durability, poor thermal shock resistance, and larger coefficient of thermal expansion. And second type of glass is borosilicate glass. Example, it is used for labware and kitchen glassware. So the advantage is very good thermal resistant and low coefficient of thermal expansion.
Of thermal coefficient. Okay, thank you. Also, that's basically this thing. So let me put this thing first. Okay, this is we have done for our class number 4. So bonus mark I will put later lah. I put later. You check those who get bonus mark today, please check. Maybe some of you there are 2 Irdina. I know only 1 Iwana, but maybe there are 2 Irdina, 2 Ridwan or whatsoever. So you check later on. So I will upload this thing in this thing. What you call the link and also the notes. So I think for that we recap just for a while. So we have learned today what we have learned. We learn about the ceramic only. So first we learn about the definition of the ceramic. We have learned about the mechanical properties of the ceramic. We learn about the Dalgona, meaning that because we want to see the analogy between glass and the ceramic crack propagation. So about the glass cutting, we also learn about glass cutting. We also learn about how ingredient to make a glass and 2 type of the common glass. There are many type, but this we are focusing only 2 type only. And we learn about the what we call the thermal resistant, low, what does it mean by coefficient of thermal expansion and so on. So I think that's it for today. So yep, it's already 9:38. So sorry for taking 8 minutes more. So for that, if you have any question, you can WhatsApp me. So for that, we end our session with recitation of Tasbih, Kafarah and Suratul As.